Welcome to video number 13 for Physics 102. This video introduces us to a new concept, momentum. What are the goals of this video? Well, I hope that by the end of this video you have some understanding of what momentum is, understand what it means when we say that momentum is conserved, know at least one type of problem for which momentum conservation is useful, and be able to apply momentum conservation to a few simple situations. Let's begin by thinking about conserved quantities. We've already talked at length about one conserved quantity, energy. Are there other conserved quantities in physics? Are there other quantities where its value before and after are the same? Yes, a new quantity called momentum. Momentum is a vector quantity that is an object's mass multiplied by its velocity. Remember, velocity is a vector. Mathematically, we write momentum as mv, and we assign momentum the letter p. Since momentum is a vector, we give it the little arrow symbol on top. This combination of m times v may be familiar from our very first definition of force that we encountered in this class, where we had F as the limit as delta t goes to 0 of delta mv over delta t. This mv in here is actually the momentum. We'll explore this interpretation of force a little bit more later in the unit. Like energy, momentum is also a conserved quantity. The sum of all the momenta before some process must be equal to the sum of all the momenta after the process. Unlike energy, however, momentum is a vector quantity, having multiple components. Here we have a momentum vector expanded out into its components. You have an x component, a y component, and a z component. When we say that momentum is conserved, we mean that each component is conserved separately. Therefore, the sum of all the x components before some process must be equal to the sum of all the x components after. Same for the y direction. And same for the z direction. In this class, we will not explore problems that exist in 3 dimensions, so we won't need a z component. We'll only need x and y. Now you may be asking yourself, we already have 2 concepts, forces and work and energy. Why do we need yet another concept? The reason is that there are types of problems that are difficult to understand using forces or work and energy. Here's an example of such a problem. We have a 2,000 kilogram cart traveling at 30 meters per second that's going to smash into a 1,000 kilogram cart at rest. The 2 carts glue together and travel off to the right with some final speed that is unknown. If we wanted to solve for this final speed using forces, we would have a really hard time because we don't know how to describe the forces that are making the 2 cars stick together. So it would be difficult to do the sum of the forces on the left-hand side of Newton's second law. Moreover, the forces are very likely non-constant, so we cannot apply our kinematic equations. So if forces don't work, what about work and energy ideas? Well, how would we handle the potential energy of the glue making them stick? Is the glue even a conservative force? Can we even talk about potential energy in this case? Moreover, the distance over which the glue is working is very, very small, so the work done will be very, very difficult to calculate. So we can see that this particular problem is going to be pretty much unsolvable using forces or work and energy. Thus we need this new idea, momentum, which makes this problem much more straightforward. Let's define everything as happening in the x direction and make the positive x direction going to the right. If this is true, then our momentum vector only has x components. Initially, what do we have? We have the 2,000 kilogram car, which we'll call m2 to remind us that it's the 2,000 kilogram car, traveling at some initial speed of 30 meters per second. In terms of its momentum, it only has an x component, and its momentum is m2 times v sub 0, which is its speed. Notice that the momentum on the left-hand side has a whole bunch of subscripts. We have p for momentum, then we have the subscript 2, indicating we're talking about mass 2, we have a subscript I, because we're talking about what's going on before this interaction. And then we have a subscript x, meaning we're looking at the x direction only. This problem only has an x direction, but latter problems will have both x and y. The 1,000 kilogram car, which we'll call m1, is initially at rest. So the momentum of 1 initially in the x direction, which is what this symbol P1ix means, is the mass of 1 times the initial speed of the 1,000 kilogram car, which is 0. Thus we get that the initial momentum of mass 1 in the x direction is equal to 0. After the interaction, which we call a collision because it happens very, very fast, that's all a collision is a very fast interaction, what do we have? We have two cars glued together into one object with a total mass equal to the sum of the two masses. And this total mass is moving along at some final speed, vf, that we're looking to solve for. So the final momentum in the x direction, which we write mathematically as p sub f sub x, is equal to the total mass times the final velocity vf. Since the total mass is m1 plus m2, we know that the final momentum is m1 plus m2, the quantity, multiplied by v sub f. Conservation of momentum states that the total initial and final momenta must be the same. Expanding this out, we know that P2ix plus P1ix must be equal to Pfx. This is what we mean when we say conservation of momentum. We're looking only in one direction at a time, the x direction. We're adding up all the momenta before the collision and all the momenta after the collision and setting them equal to each other. For your quiz, you will be given values for the speed of the moving cart, the mass of the moving cart, the mass of the stationary cart, and you will be asked to chug through the algebra to solve for v sub f. This concludes this video.